Thank you for coming. This is part 2 of the 3 lectures on density methods by Professor Ole Sigmund. So the last lecture was highly visited and anticipated. So we had 226 in the audience online, and the YouTube video has been available ever since, and it has been watched quite a lot. And the plan is for today's lecture will also be on YouTube, and that's how we'll be moving forwards. So just like last time, I won't give Ole the full introduction, but Ole, especially relevant for today, is the inventor of the sensitivity filter and the so-called robust formulation and many other things. And today Ole will be diving into filtering and geometry control. And the lecture will be around 50 minutes, and we have the question and answer tool going on download. So in the bottom of your screen, you should see a little Q&A with like a speech bubble with a question mark. So if you type in your questions there, then we will take them at the end. And please already, if you find a question during the talk, you can already write it. Last time, all the questions came dumping in at the end. That's also okay, but you can just leave your question as soon as you get it. And with that, I think I'll hand it over to you, Ole.
Okay, thank you so much again, Joe, for inviting to give these tutorials. And I've really been looking forward to this. And it's also a good occasion for myself to sort of collect thoughts into 3 consecutive tutorials. So today we have arrived at the wonderful world of filtering. And just to, let's see if I can, so last time I introduced the basics and of the density approach. So if you are new or if you are watching this on YouTube, I'd recommend to go back and watch that, the first one first, because today I'm building on top of that. But nevertheless, let me just start with 2 slides to remind you of the main conclusions from the first tutorial. So first of all, we landed at the density or SIMP approach to topology optimization. So that's where we discretize the design domain and have one relative density variable per element. We interpolate the stiffness as a function of the density with this power law approach, where P, we also showed, P equal to 3, actually gives a physically realizable interpretation of the microstructure also. And this realizability is also something I will come much more back into in the third tutorial. So this was a parameterization. So we have a number of elements, design variables, and then we can design an optimization problem minimizing some function of the state and the design variables rho. We typically have a volume constraint, and then we could add a number of additional constraints. And then I'm indicating that we are solving a finite element problem at the outside that feeds sensitivities into the optimization loop. And also a nice thing of the density approach is that the stiffness matrix is a summation over each of the elements and their dependence on the density. So this is the general formulation, and that can be put into a flowchart like the following. We initialize with typically a grayscale material, then we do some filtering, finite element analysis, sensitivity analysis, back filtering or chain rule, then we optimize and we update the variables. And a very powerful point is that we can find the sensitivities using the adjoint method, which means that no matter how many design variables we have, we at most have to solve one extra analysis problem or one extra right-hand side in order to obtain all the sensitivities. So this is the general approach here. I'm not going to go deeper. If you want to know more, then check the first tutorial. However, in the first tutorial, I went very briefly over the filtering aspects, so with the filtering and this back filtering or back propagation part here. So this is actually the main thing of today. So the main purpose of the filtering at least back then, was to ensure a certain length scale or eliminate mesh dependence. So we saw that if we solved the same problem on finer and finer meshes and didn't do anything to avoid mesh dependence, then we would get finer and finer solutions. They are also better solutions, but they could also be more expensive to fabricate. And we would also like to have an accurate finite element analysis. So somehow we wanted to introduce something that avoids getting finer and finer structures when we refine the mesh. And so the idea was to introduce some kind of restriction or regularization that ensures a certain length scale. And in that way, when we refine the mesh, we get better and better description of the boundaries, not more and more details. So I also briefly touched on the sort of main methods, and so we call them filtering approaches in topology optimization. And here there are sort of two main approaches, either image-based or PDE-based. And actually those two approaches are also divided into sensitivity filtering and density filtering methods. So today I will actually not talk about sensitivity, or there will be a single picture of it, but I will actually jump directly to density filtering because that provides the basis for the more advanced filtering approaches I'm going to talk about. So for the density filter, the original filtering was based on image filtering, or we call it image filtering because it was originally based on ideas from noise suppression in image processing techniques. Then to introduce a length scale, we introduced a filter that is independent on the finite element mesh. So that introduces a radius that will control the minimum length scale in our structures. And hence the filter is about finding the elements within the neighborhood of a certain element and then smoothing or averaging the local density over these neighboring elements. So this works quite well, but alternatively, and almost with the same results, we can use the so-called PDE filtering. So instead of looking for neighbors and averaging, then we solve a diffusion problem, you could call it, where the design variables rho are on the right-hand side, and then we solve for the filtered variables. And that actually is just a scalar problem, so it's often much cheaper than solving the actual physical PDE we are looking at. And there is a direct relation between the radius or the length scale in the PDE filter and the radius or the length scale in the density filter. Implementation-wise, they are fairly easy to implement both of them, or definitely the image-based filter. So essentially you make a neighborhood matrix. So that's a matrix that for each element finds the neighbors that are associated with that element, and you put the weightings in there. And then you essentially just multiply this, your design variables with this neighborhood matrix, and you get the filtered variables. Then when you have done this filtering, then after finite element analysis and computation of the sensitivities, you have to do the chain rule to find sensitivities with respect to the original design variables that you are going to use in the optimization step. So this is image-based technique. In the PDE filter, well, you have to do a couple of things. So first of all, you have to build a finite element. You could call it diffusion matrix. So it's for a scalar problem again. It's much cheaper than the real physics problem. And the nice thing is that this matrix only needs to be built and factorized once. Then its factorization can be used to do all filterings and back propagations in the rest of the optimization. So really, it's not more expensive. And you could also say, so the two filters are performing pretty much the same, but there are certain advantages with the PDE filter, partly for large 3D problems, because actually just finding all the neighbors can be a big process, and this neighborhood matrix can become very big. It's also a problem if you're doing parallel computing, because you don't want to have interaction between subdomains. And there are also certain cases when you have complex domains and like with small cracks or small features, then the image filter would be filtering across these gaps, whereas the PDE filter filters around the gaps, and in that way it makes more physical sense. But really, the differences are not big, and so in the rest of this tutorial, I will not really discuss whether I use the PDE or the image-based density filtering. But let's apply this to something. And I could, of course, continue with the MBB beam that I looked at last time. But as I said, that's also too easy. We have to make life a little bit more challenging for ourselves. And a very good sort of step 2 when doing topology optimization is to look into compliant mechanism designs. And that also turns out to be a very good demonstrator for filtering techniques and their importance. So a compliant mechanism is a mechanism that doesn't have hinges or ball bearings or anything like that, but it achieves its mobility by compliance or bending of the structures. And we can define a design problem where we have a design domain. We have an input actuator. It could be a piezoelectric, a shape memory alloy, or something like that. And so that would be pushing on this domain. And then we want to perform work on some kind of workpiece. And so it's not more much specified, but something where it has to generate a force or displacement. And in this case, we actually want to push to the right with the actuator and then pull the workpiece. So this is a very nice and challenging second topology optimization problem. What we typically do is use symmetry, and then we model the input actuator as a spring, and actually also the workpiece as a spring of a certain stiffness. And sometimes in literature, this is called artificial strings, but I would actually emphasize there's nothing artificial about these springs. So this input stiffness would model the stiffness of the piezoelectric actuator, so that is highly physical. And likewise, for the output part, you could have some workpiece that you want to crimp or grasp or something, and so that would also have a stiffness. So this is a purely physically motivated formulation of the compliant mechanism problem. If we formulate the optimization problem, then I'm just following the setup that we have seen before. So in this point here, we are going to minimize the output displacement. So minimize the output displacement means maximizing in the negative direction. And that we can obtain by writing or defining an L vector. So that's a vector with zeros, except for the degree of freedom where we want to minimize the output displacement. And hence it picks out the relevant degree of freedom of the system displacement vector. Then we solve the usual finite element problem. So it's very much like before. We just add the two springs that we added for the inverter mechanism. I'm putting a star here saying that actually we should always use geometrical nonlinear analysis when we do mechanism design, but that's really not the main point here. So today I'm just going to assume it's a linear problem. Then following the adjoint analysis scheme, then the adjoint problem becomes this one. So remember, it's the derivative of the objective function with respect to the state vector. And so that's simply L, and then with a minus sign. And so the adjoint problem is the same as the original one, but just with a load corresponding to a load at the output point where we want to minimize the displacements. And again, following the rules, then we get sensitivities that the derivative of the objective function, so the output displacement, is simply the mutual energy or the adjoint, the solution of the adjoint problem, times the derivative of the stiffness matrix with respect to that variable and the origin solution. And so that's actually all there is to it. So compared to the MBB beam, it's just a few extra lines in the code. So if we optimize that using all the state-of-the-art of filtering that I will come back to, then we will get a mechanism looking like that. And if we actually remove the upper part or we reintroduce the upper part, then we can operate it. And we see here that we get the desired kinematics. We also see that we get a beautiful black and white structure, or almost black and white structure. And we also notice that there's not sort of very concentrated or one node connected hinges that you will see in many places, because that has been taken care of by the filtering strategy that I'm coming back to. So this is sort of the goal. This is the kind of mechanisms we are going to use as demonstrators in the following. So now let's step back a little bit and say we don't do the state of the art, we just do density or sensitivity filtering of the problem. And so in that case, the designs look a bit worse, right? So they don't have the nice, clear black and white features. And you see here that it has very concentrated hinges. They look a bit different whether you use sensitivity filtering or density filtering. Sensitivity filtering has these one node connected hinges. Density filtering has gray hinges, which are not much better. So really using just simple filtering, whether it's density or sensitivity, does not really give us useful designs. So what can we do against that? Well, the first thing we could take care of was to try to get some sharper boundaries that will make it easier to sort of extract the actual geometries. And how to do that? Well, the obvious thing is to do some thresholding. And so now I'm switching the graphics a little bit, but you would sort of see here I'm showing the original design variables and the filtered field as some 3D plots. And you could imagine, so that's a cross-section through the structure that I optimized. And so in this case, I'm using density-based PDE filtering, but we could also use the image filtering. So this gives us the gray transition regions, and it gives us the gray hinges. So to get rid of that gray, we could make a threshold. And so we could introduce a Heaviside function, or we could call it a projection, or probably mathematically more correct, a mapping function, where we threshold at a certain value eta between 0 and 1. And so everything, all filtered densities below eta go to 0, and all above go to 1. And then we would get a nice looking picture, very sharp, black and white. However, we also see here that we almost disconnected the hinges, and they don't really become physical hinges. So we would actually, so we cannot just post-process. So we want to include this thresholding in the optimization process. However, we are using gradient-based algorithms, so we cannot have a sharp jump that would make it non-differentiable. So we make instead a smoothed Heaviside function. And so the much used smoothing function is this tangent hyperbolic function that is a function of eta. So that would be the threshold value where we make black and white between. And then there's a beta coefficient that determines the sharpness. So if beta is 1, then essentially it's just a linear projection or mapping. So nothing is happening. It's just a density filter. But as beta increases, then we get sharper and sharper, and we would expect that the design gets more and more black as we increase beta. And so in practice, to avoid getting stuck in local minimum, we have, up to now at least, been using a continuation strategy. So we start with beta equal to 1, then it's a nice and smooth and well-behaving problem, and then gradually we increase beta to a higher value to end up with black and white solutions. How big beta max should be is something I'll get back to later on, but that's the general strategy. So if we do that, well, sorry, first just a few words about how to implement it. So now we have that the physical density is a function of the projected filtered field, and the filtered field is a function of the design variable. So in that sense, when we are doing the computations, we would start the design variables, we would do filtering, then we would do the projection to get what we call the physical field. That's the physical field, or physical design variables are the ones we send to the finite element analysis. Then we do the sensitivity analysis based on these physical variables, but then to do the optimization, we have to backpropagate or use the chain rule to get the sensitivity with respect to the original design variables. So in that way, we get a consistent sensitivity analysis. And the nice thing is actually that we don't have to do much. We just have to do a pre-filtering and then this backpropagation afterwards to obtain the sensitivities and run the optimization. So that's sort of the way to implement it. Now let's try to run it for the mechanism problem from before. And in this case here, I'm running it with 3 different values of this threshold here. And if we take a look at the 3 designs here, well, let's start in the bottom, because that was the original introduction of the projection method by Jamie Guest. So we look at the mechanism and see, hey, we did get rid of all these gray transition regions. So in that part, the filter was successful. However, if we look at the hinge here, we see sort of that we didn't really get rid of it. And interestingly, so the red dot here is showing the radius of the filter. So that gives us a length scale. And you could look at this mechanism and see, hey, this is actually a mechanism or a structure that can be built by deposition. So like with a toothpaste or something like that, you deposit, or like a fuse deposition AM process, we could process and add material with a nozzle that has this diameter. However, we also see that there's a very bad hinge here that would break or get disconnected as soon as we would use it. So really, using the projection filter with eta 0 would not work. Then we could go up and say, hey, we try to use the projection with eta equal to 1 instead. So we call that the erosion filter. And if we look at the obtained structure, again, it's black and white. However, it still has these very thin regions here. So it would still not be good. But what we also notice is that this could be called a machining filter because there are no void features anywhere in this design that cannot be manufactured by some machining tool that is cutting away material here. So they both have two very distinct features, but none of them do very good. Then we could select to threshold at 0.5 as suggested by volume preserving filtering techniques. Again, we see we get very nice black and white, but really we lost the length scale. So that wouldn't work either. So we have 3 filters with each their special feature, but none of them in themselves are doing well. But that's what made me originally think, hey, what if we combine the 3? So instead of just optimizing for one of them, we optimize for all 3 of them, and we optimize for the worst performing structure subject to each of these 3 thresholds. And so this is what I call the robust topology optimization formulation. So again, we have our design variables, we have the filtered variables, but then we do this thresholding. So we threshold at 0.5 density, then we threshold further up, delta eta up. That would be what we call the eroded structure. And then we threshold lower, and that would be what we call the dilated structure. And we can actually do all kinds of proofs of what the difference between those 3 levels will be when we know the filter size. And so we should be able to say something about theoretical length scale and stuff like that. So we now optimize for 3 different structures. And so the optimization problem now becomes a min-max problem. We minimize the worst case of these 3 realizations. We call it the intermediate, the dilated, and the eroded. And so we need to do 3 finite element analysis per iteration. So that's much more expensive, but as you will see, it's also worthwhile. Then our volume constraint from before, we should in principle also have 3 volume constraints. However, we know that the thickest structure, the dilated structure, will always be the most active one. So we just need to optimize for the dilated structure. And what we often do is then that we adapt this V star to the volume of the intermediate structure, because the intermediate one is the one we are going to realize. And so we do that on the way in the optimization process. So let's see what happens. Well, here is the result of the robust optimization. And if we look at the center structure, the intermediate, or we could call it the blueprint, then this is the design that I showed in the beginning when I introduced the compliant mechanism design. And we see it's a beautiful, almost black and white structure. And we can actually prove in this case that there is a certain length scale. It turns out in this case when the eta and delta eta, when delta eta is plus minus 0.5, then we can actually say that the length scale that we introduce is half the size of the filter. But there's also other expressions if you don't use these large delta etas. So we have a very nice design, no localized hinges, and so this should be immediately realizable. However, if we are not good at realizing it, if you're going to etch it in a microscale or something like that, and we etch too much, then the eroded version of the structure will also be performing well. And likewise, if we etch too little, then the dilated will also be doing very well. So in that way, we get a design that both behaves and avoids the hinges and stuff like that, but is also robust towards certain manufacturing errors. I'll just show a picture of the convergence history here. So this is objective function. It goes in the beginning. We have a positive output displacement to the right, but soon it goes negative. And we will see here for the three structures, they go nicely down as long as beta is just 1. Then we, every 50 iterations, start increasing beta, and we'll see that there are some jumps, because we are sort of changing the optimization problem. And at some point, we notice here that the blue and the red curve start coinciding. And so that's really the eroded and the dilated. They are the two worst cases, right? If it's too thin, it doesn't transfer forces or displacements. And if it's too thick, it gets too stiff. And so therefore, a proof that the algorithm works is often that the eroded and the dilated structures follow each other nicely. At the same time, the intermediate or the blueprint is sort of taking a free ride here and is not active. So that's a special thing for compliant mechanism design. It's not always the case, so you should always check it. But if we sort of made a cross plot where we change the thickness of the structure by changing the threshold value, then for compliant mechanisms, we would see that the thicker dilated structure and the thinner eroded structure are always the most active ones, whereas the objective function for the intermediate one is actually better than the two others, but still not bad if it's eroded or dilated. This is a nice convergence curve. Sometimes we have larger jumps, and sometimes it can even explode and not do well, so there's still room for improvement. In the literature, there are different ways to improve the continuation strategy, but I will not go into that here. So this was a case, and really it behaves super nicely. And you could say in this case for a compliant mechanism design, we actually don't need to do the finite element analysis of the intermediate structure because it's never going to be active. And so with that insight, we can actually also use that for other cases. So if we do compliance minimization, so if we go back to standard stiffness optimization, then we would know that the eroded structure is always the worst case, right? The thinnest structure has the largest compliance. So in that way, or in that case, when we do compliance minimization, we could do the so-called smart man's robust formulation, meaning that we don't need to actually evaluate the intermediate and dilated structures. We can just evaluate the eroded one and then run it subject to a volume constraint on the dilated one. So that gives us a very efficient procedure. And in this review paper, we actually did that partly for the L bracket example and partly for the thermal problem. And we see, again, we get very nice black and white solutions. An interesting point here is that when we use, in general, the robust approach, but also just the smart man's approach, we can actually run the problems without penalizing intermediate densities. So these were run with the same procedure with p equal to 1. And so that's kind of a little bit mind-boggling. But the thing is that the robust formulation promotes black and white. Because if there was any gray in the dilated structure, which is the one that counts in the volume constraint, then that gray would disappear totally for the eroded structure, and thus the eroded objective function would be really bad. So in that sense, there's a motivation through the robust formulation to create black and white. And in the extreme case, you could say we can drop doing penalization in the usual SIMP sense. However, it also has some disadvantages, or there's sort of a tendency that the black and whiteness happens suddenly for a certain value of beta. So I would not in general recommend it, but I would recommend it for very sort of challenging problems where you have problems with a grayscale. Then a smart man's robust formulation might actually help you a little bit. So you base the objective function on the eroded, or it could also just be the intermediate. But then you put the volume constraint on a slightly dilated version, and that will do wonders, I promise you. Okay, so that's an interesting observation. I would just also say we in this paper, we included the grayscale measure. And so this is a measure, you could also call it a measure of non-discreteness. So we sum up over all elements, and those which are gray will give a value. Those which are white or black, they will give 0. And so when we sum up and divide by the number of elements, we actually get a number that we could call how many, or what percentage of elements are not black and white. And in earlier times, that was sort of a quality stamp of the solution. Well, I guess it still is, but as you will see later, it's not as important as I think it has been. So let me go on, and before sort of adding more to this, then I will just show you a very nice example that also shows the importance and the efficiency of the robust approach. And so this was a case I did with Xiaoping Jiang some years ago, where we wanted to optimize so-called electrostatic actuators. So in that case, you have a ground and you have some electrodes, and then the forces will come if there's a gap between two solid regions. Then electrostatic forces will make a contraction force. And interestingly, this force is proportional to 1 over the gap size squared. So that's a very strong promoter of having a very small gap. And in that sense, it's a very mesh sensitive problem. The smaller the mesh, the smaller the gap, the better the performance, but the more non-physical the solution gets. So we made one design without any robustness or anything like that. And you see here that you get this one element wide gap region that gives you some very artificial and non-physical forces. However, with the robust approach, we got this neat, well-defined gap that has several elements across, so you can actually trust the electrostatic forces. And if you then animate this structure, you would see something like this. So this is one case of the benefits of using the robust formulation. So it cleans up, gives nice and black and white structures, it introduces length scale, and it avoids various sort of non-physical problems in multi-physics problems. Okay, so now I've sort of made a teaser to it earlier. So how black and white do we actually need solutions to be? So if you read the early papers, also the 88-line code where we actually give you the code for the projection, then we used beta max values up to 512 and got entirely black and white solutions, and we're proud of that. But to be honest, maybe it's my age, I get more mellow and I get satisfied with less than that. Because actually, why do we want to have absolutely discrete solutions? Well, we want to have that if we have in two cases. Partly, if we want to compare our design with another approach, then it's important that we only have black and white, because if we have different interpolation laws, they are not comparable. Or there could be very special physical situations where we can only model the correct physics if it's completely black and white. But otherwise, in a way, the most cases, we actually don't need that. What we are interested in is having a little bit of grayscale, because that promotes smooth convergence. And so we can stop when we have converged well. But then what should the value of beta be, or beta max be? Well, if we go back to a paper we did with Gustavo da Silva some years ago, then we took a look at the smoothed Heaviside projection and said, well, what, a little bit like level set people, what value of beta gives us a transition region or a gray region that is around one element wide. So if this is one element, we are asking what's the value of beta that gives us a slope that ensures a one element transition region. And it turns out you can do that analytically, and you can find what we could call the beta lim value, the limit value, which is 2 times the filter radius divided by the element size. So that would give us designs that have a transition region grayscale of one element. And that's exactly what I used over here. And so if we make an enlargement, we will see here we have a bit of grayscale. And so that ensures that we converge very well. It's a smooth convergence still for the larger beta values, but we don't need to go further like that. And the other nice byproduct is that if we want to actually extract the geometry, we can run a level set or a contour plot and extract the topology from that and get very smooth surfaces. So that's a general recommendation I'm giving to people these days. Don't use beta larger than 2R over HE. And there's actually some extra insight in there, because this actually gives us a fairly strong projection here. And you could also say outside this, one or two element wide transition region, we have zero slope, which means that the sensitivities become zero. And so interestingly, you could say starting with a large beta value is very much like running a level set method. And so I will actually show you in this animation here that density approach is nothing but a level set method or opposite if we run with beta value equal to this beta lim value I've just demonstrated from the start. So this here shows 3 initial guesses for the MBBB, 5, 6, or 7 initial holds. I'm going to run it. This is essentially just the 88-line code, however, with a large beta value. So the beta value in this case, I think the discretization is 200 by 1200 elements here. The beta value is 22. And so let's see what happens. I run them at the same time. And you see here, there's no grayscale ever. Everything is running. And if I hadn't told you and promised you, then you would think it was a level set approach I was running. But this is just the density approach, run with the 88-line code with one change to normal, which is run with a large beta from the beginning and have these starting guesses with 5, 6, or 7 holds. So I think that's an interesting observation. I've always said there's not much difference between density and level set approaches as long as the mesh is fixed, and this pretty much proves it. Okay, so this was the generally recommendable beta value. And let me go on. I see that the time is running. But a few more words here, because this beta value, sometimes we actually want to run with an even lower one. And that dates back to a study with Gustavo da Silva, so that's also the one I referred to before. But if we want to do stress constraints, it's also important that we have smooth behavior of the stresses, especially if we run it on a fixed grid and evaluate the stresses in the centers. So we did this fixed grid test case where we took a hole. We know what the stresses should be, but with a fixed grid and these jagged edges, they will probably be very oscillatory the radius. And so in this case, this is the maximum stress at the point here in the discretized or the fixed grid as a function of the radius, and we see these spikes. And so that's every time the radius or the circumference is passing one element boundary. And this would obviously give very bad finite element convergence. However, if we then do the filtering, so the density filtering and projection with the recommended beta lim value, then we see that the stresses get much smoother. If beta is 2 times b lim, so that would be a transition region of half an element, well, then we still have quite strong jumps here. If beta is equal to beta lim, we get much smoother behavior. That could be good enough, but actually in that paper, we ended up suggesting beta to be beta lim half, because then we get almost a perfect smooth behavior here. And so together with the stress interpolation, then we were able, again, with allowing a little bit of grade transition to do the optimization, in this case, minimizing the volume subject to a stress constraint. This is the stresses evaluated on the fixed grid. Then we put in a contour through density 0.5 and did a body-fitted mesh with very high resolution, but otherwise no post-processing. And we got almost the same stresses with this beautiful structure here. And well, to test how robust it was, we also tried to erode and dilate it, and we plotted that performance. So we saw that we optimized this without a robust formulation at eta 0.5, and we got a perfect performance here. But we also see here, if we just do a slight erosion of this structure, then the stresses shoot up. So this shows we can directly extract topologies that actually have the right physical stresses from the fixed grid topology optimization approach, but it also shows that we do need the robust formulation also in this case. So we reran the example, so this is still the deterministic one, but then if we reran it with a robust formulation, we see this is the structure obtained. And very interestingly, in this case, we just optimized it for 3 eta values. But if we make a smooth erosion or dilation of the structure and calculate the stresses, well, then they stay totally constant, both in the fixed grid, but also with the diamond structures here in the actual body fitted mesh. So I think this shows that with the appropriate choice of filter and projection settings, then we can actually extract structures and get perfect fits in post-evaluations. Okay, so now this was the standard robust approach. I still have 10-15 minutes here, so let me proceed to slightly more advanced filtering. So the first one is the original robust approach just considered erosion, dilation, uncertainties. You could also ask, hey, some processes are more random, so there's random perturbations of the boundaries, and it turns out we can actually model that with almost the same approach. However, instead of making this erosion, so changing the constant level of the eta where we threshold to get eroded and dilated structures, then we make a random surface and use that to threshold or smooth threshold. And in that way, we can get random perturbations. And so we use a so-called Kahune-Löw expansion where we decide the correlation length, and then we do an optimization. And so originally we did it as a Monte Carlo simulation. So for each optimization step, we did 100 different realizations of the structures, did 100 different finite element analysis, and then found the average of these values and optimized the mean value plus some factor times the standard deviation. We have since then tested various other stochastic collocation and perturbation and stuff like that. None of this is super successful, but so for now I will just show you this Monte Carlo result. So this here is now a force inverter, still a compliant mechanism, a gripper, still a compliant gripper, and it's first optimized for the deterministic design, and we see we have these issues with the thin hinges. And then if we do a post-evaluation with these random perturbations, so these random thresholds, then we will see that if we have the wrong perturbations, then the structure actually gets disconnected and the performance, the average performance is really lousy. Then if we do the Monte Carlo-based optimization, where we take these uncertainties into account, the objective function, the mean value, is a little bit worse than before. However, if we do the post-evaluation, we see almost perfect behavior, and we see a structure that's actually robust to all these different perturbations. Interestingly, if you compare this to the simple robust with erosion dilation, there wouldn't be much difference. So for compliant mechanism design, we don't gain much. But if we look out in the literature and recent studies, we will see, especially for wave propagation problems, that these perturbations and this randomness is quite important to get better designs. So I've shown a couple of different approaches, also some by Kriegesmann and co-workers, where they're doing more efficient perturbation approaches and stuff like that. I think there's a lot of activities and a lot of interesting things to do in that area. So I'm recommending it for further research. Okay, so now this was the robustness. Let me just use the last few minutes here on showing some more advanced filtering approaches and how you can play with filter techniques. And so the first thing is coding. So we have seen many examples. Also, nature has bones where the outer shell is stiff, and then you have a porous, spongy inside. And we were thinking, can we do that and also make use of these spongy insides and stiff outer parts in topology optimization? So can we find a formulation where we actually control that? And this gets complex. I'll just go quickly through it. But so essentially, we start with the design variables, we do filtering, and we do projection. Then we do a second filtering step with a smaller filter. We compute the gradient norm of that step there, so that identifies where the boundaries are, the gray transition regions, and then we threshold that also. And so that actually identifies the outer edges of the design. And then if we take those two fields, so the original field and this boundaries stuff together, and do an appropriate Young's modulus interpretation, then we can actually start doing design that has these edges outside, or the interface is solid, and the inner part with a certain porous stiffness, without having extra design variables. So still just with one field of design variables. So this is one way to do it. There's another which may be a little bit smarter. It's essentially doing the same thing, but instead of doing the computation of the gradient norm, it makes a second erosion step, subtracts those two structures, and identifies the edges in that way, and then uses a similar Young's modulus interpretation. So those two approaches makes it possible to do beautiful things where we have this control the inner stiffness and control the outer region, or the crusts. You can control the thicknesses of these crusts, and you can do various studies where you're looking at the influence of having different infill stiffnesses. So in this case here, we get less and less stiff infill stiffnesses, but also interestingly less and less stiff structures. So it's not an advantage to do this from a compliance perspective, but it then turned out that from a buckling perspective, by having the thicker structures that have internal porous structures, well, then we could actually increase the buckling load with a small decrease in the stiffness. And many people have or are extending these ideas. You can use it to make multi-flow design, both in density and level set approaches, and you can control gaps between electrodes and stuff like that. So again, an interesting area for further exploration. And also you can use it to control overhang, and I will not go deeper into it, but this was work with Xujian Liu, where we are using these multiple projection strategies to also identify the overhang regions, and in that way design structures that are don't have problems with overhang for additive manufacturing. And so speaking about this year, this is a huge field. I think one of the main contributors is probably Matthijs Langelaar. If you want to find a review on this, we have this quite formidable paper that has 1164 references, not all to AM constraints and filters, but it's definitely worth looking at, and also consult some of Langelaar's work that show how you can use filtered strategies to control geometry in topology optimization. Okay, just a few last pictures here before the end. So the last topic here is what I call a local volume constraint, where we go back to the original compliance formulation, but we add an additional constraint. And so this additional constraint is also sort of a filtering thing. So we do a filtering with a large filter on the already projected design row bar here. And then we say that the average density in under the large filter has to be equal to some non-local volume fraction constraint. So in other words, we can say if we have a magnifying glass over the structure and put rho C to 0.5, then we want to have a density within this magnifying glass of 0.5. And we introduce that as an extra geometric constraint as a p-norm approach. And the beauty is the following. If we look at the left side, we would get sort of a standard compliance optimized design for a bone-like structure. But if we introduce this local volume constraint, then we will see that due to this constraint, it says there has to be material everywhere with a certain density under this larger filter. Then we get these beautiful sort of porous structures. And this can be done in 3D also. The picture to the right shows the optimized structure. We have realized it, and it works like a charm and produces very interesting structures. And so then you can actually take that interface approach that I showed you before and combine it with this infill optimization approach. And this becomes a filter extravaganza. I think there are like 5 or 6 filters and 5 or 6 projections and all kinds of combinations. You would think it's impossible to make this work, but this animation actually shows that you can do design where there is a fixed outer crust of material with a certain thickness, and then you also have this local volume constraint, and you get these beautiful sort of multi-scale structures. This is for the single load case problem, and in the other case, you have a multi-load case problem where you see different features. And so you could sort of say, now this looks like multi-scale, and so this bridges to actually tutorial 3, where I'm going to talk more about multi-scale approaches. And so this brings me to the end. We also did it in large scale with PDE filtering, making these beautiful plane structures. But let me get to the conclusions. And if I would just say one line, then filters provide seemingly endless opportunities in topology optimization. And I invite you to have fun with these things. I have some more comments, like geometry can be strongly controlled by appropriately applied filtering strategies. The robust approach, I'm a big favor of it, despite its limitations in some cases, but that delivers robustness and very well implemented length scales. Then I asked the questions, do we really need 0,1, or should we stick with almost 0,1, like the majority of level set approaches on fixed grids? And SIMP-based filtering projection methods are very similar to fixed grid level set. I showed you that with the examples. So I think we should stop discussing differences or discrepancies between the two approaches. They are really just one and together. And then finally, I've shown you how a local volume constraint favors some anisotropic microstructures, but it's very expensive. So that's leading to the third tutorial on how to do efficient multi-scale approaches. So thank you very much for your attention here. Again, I have some fairly ego-centered papers here, but there's so much literature out there. And if any of you have questions or need extra references, you're very welcome to also contact me with additional questions. So thank you very much, and I'm ready for questions if anybody has.
Okay, thank you, Ole. So we have a few questions already, but if you have any questions now, please fill them into the Q&A box at the bottom. There's a little button with Q&A, and you can type in your question. So we can start with the question, which filtering approach would you recommend if the material is non-linear? Does it make a difference with this image-based or the PDE version?
I think that's totally material agnostic. I wouldn't recommend one or the other. I'm sort of getting more and more in favor of the PDE approach because it's more efficient for large-scale problems, and it's sort of just using the already existing finite element mesh. But I don't think it will make any difference whether you use one or the other.
Can we use the total variation regularization technique as an additional term in the objective function? And does it have a similar effect as the filtering methods?
Oh, definitely, yeah. So there are other techniques, and I should maybe have mentioned some of them. So the total variation has been tested in various ways. So depending on how you do it, whether you count smooth gradients or only the boundary length and stuff like that, it has different features. Personally, I'm not in favor. If I can avoid it, I don't want to add anything to the objective function. So that's why I like the filters, because they are sort of, as I also wrote in the second point here, geometry can be strongly but indirectly controlled. So I'm much in favor of that. As soon as you add something to the objective function, it becomes important what the weighting factor is and stuff. The other thing is that there are some of these other, like the perimeter control, which in some sense also can be called a total variation approach, depending on how you see it. The perimeter control controls the length of boundaries, and in that way also introduces some kind of regularization. However, the perimeter doesn't care about hinges, because they don't really add extra length or extra boundary length. And hence, perimeter control does not resolve the localized hinge issue in compliant mechanisms. So in that sense, filtering have a local radius that it enforces, and in that way controls geometry better.
Okay, and then we have a question from Fabian Wein. So does the level set SIMP method lose the SIMP feature to generate void and solid everywhere?
So you could say here, I didn't test it, and it's a good question, but I think I could run it with p equal to 1 and get exactly the same. I did use p equal to 3. As I said, I didn't change anything else but running with a larger beta value. But I'm thinking that actually it might work better with p equal to 1 or even more smooth. But let's try it. I guess we can all go back and do it because it's really not much change in the 88 line code.
Yeah, actually, that was basically my question too. I think if you run it with p equals to 1, you'll get grayscale everywhere, right? If the problem really wants grayscale, then don't you think
Yeah,
grayscale would
maybe
appear?
if you run it long enough, right? But the thing is that if you have this high, fairly sharp threshold, then you put the sensitivities to 0 in the void and solid region. So you really only have sensitivities in the gray region. But it's an interesting question. So maybe we have to try it.
Yeah.
So with you can do the smart man's robust. Then it shouldn't be a problem for sure.
And I guess one benefit of this would be that you could actually also start with a uniform grayscale, right? Which you cannot with a level set method.
Yeah. So we of course maintain the original benefits. Again, I don't want to start. I don't want to be mean to any methods here. I'm sort of just saying that the differences are very small. And I think previously, historically, or still in many papers, people write, I'm using the level set approach because it gives me black and white designs.
Yeah.
And I think really that's not a reason to use level set methods.
Right.
Because we can do that with density approaches also. But yeah.
How much more costly is the non-local volume constraint?
Well, in principle, it's not costly at all because it's just an extra constraint. So it's one filtering step and one additional constraint. Problem is, it's a p-norm constraint that sometimes is a little bit sort of depending on how high p is, it becomes non-differentiable. So you may need more iterations. So I think it's not more iteration-wise. It's not more, or what you call time per iteration wise. It's not more expensive, but you probably need more iterations to make it converge.
Then we have a question from YouTube here. So do you have any opinions on explicit topology optimization methods, such as moving morphable components?
Yeah, good question. So this is a tutorial on density approaches, and now I've been venturing a little bit into level set approaches. So morphable components is a beautiful thing because you can sort of say, if I want to build a structure that has certain components, then you can use those, and then you will not end up with weird shapes or uncontrollable shapes, or I shouldn't say uncontrollable, but more complex shapes. So in that sense, they are good. And I would also say that moving morphable components is using the same concept of this beta lim, because they also want a little bit grayscale at the edges in order to get sensitivities that actually drive the motion. So definitely, I haven't done much with morphable components, except in some cases, if you have an actuator. We had a morphing wing design thing, where you have a fixed actuator and you let that move around, and then we had the density approach around it. So that was definitely very nice. And I'm also doing some work with Julian Morato these days with morphable component methods. But yeah, so I think they are great for their purpose. But for me as a researcher, I am always in the favor of getting the most possible design freedom and not constrain too much if it's not required. But yeah.
For the stress constraint problem, even with a high projection beta, I can see many intermediate design variables. Is there any approach to resolve this? So I
I'm
think
not.
maybe it's based on their own personal experience, I
Yeah,
would
I
assume.
think it's so now. No, I don't think we see that. There were a little bit in one of the examples in the not robust design. I will not go back and look at it now, but I think with the appropriate choice, so definitely with the robust helps there,
Mm.
and using these recommended settings for the ramp interpolation of the stresses and stuff, we didn't really have a problem with that. It is a more difficult problem again because you have more constraints. You have either a p-norm or an augmented Lagrangian approach, so it needs more iterations. But I wouldn't say that in general you get more grayscale.
Okay. And then we have one last question, at least for now. I'm a beginner in design optimization. Do you have any suggestions on where I should start? Any resources that you would recommend? And maybe I can first say I would recommend you go back and watch the first webinar. That is a great place to start. But Ole, do you have anything else?
Yeah. Well, that would also be my first part, but then also go. So it depends a bit design optimization. So do you want to actually play with the codes, or do you want to do design with topology optimization? So if you're really interested in the topic, then go to our webpage, partly download some of these MATLAB codes that I spoke about last time to get into it. And definitely also look up the top-up apps, play around with those and get a feeling of these things. If you are sort of more there for doing the actual design, then I would look up some of the, well, again, the apps for the very first tries, but then get some of the commercial softwares that are offering beautiful and very efficient solutions to advanced problems there. Yeah.
And more questions came in. So when introducing all these filters, you changed the mathematical formulation, which made me think about the divergence from your optimal design with an original unfiltered design. How do you evaluate sort of the error in between the filtering approximation versus those errors inherent to the simulation? I think that's,
Ooh, that's a lot of questions in one,
yeah.
I think. So first of all, I think the filters, if you introduce a certain length scale and thereby model all features in your design with multiple elements, then you're definitely reducing the errors in the finite element analysis. And so I think also with the examples with the stress constraints, I showed that by going from the fixed grid mesh to the body fitted mesh, we had hardly any errors. So that part of it, I think, is well taken care of and only gets better with filtering. Then, yes, every filtering thing in principle limits the design freedom, but often actually it also convexifies or smoothes the design domain. So it's actually often, if you don't do any filtering, you will get right into a bad local minimum. If you add filtering, it will keep moving. Also, as we saw, as long as beta is not more than beta lim, then it will keep moving and you will not get stuck and you will converge. Of course, I can never guarantee the global solution or the global optimum, but a much better optimum. So if you look at it sort of, if you start with no filtering, then you get a bad performance. Then you introduce filtering and you first improve performance. And then as the filters get bigger and bigger and you're losing features or putting more constraints, then you lose performance again. So there's sort of a sweet spot of filters helping you and not causing too much damage. So I don't know if that was a clear answer. It's a fairly complex answer, but filters are not bad in general for convergence in topology optimization. In the contrary.
Okay, so do you have any opinion about increasing the SIMP exponent during optimization to remove gray densities?
Yeah, I don't want to. If I can avoid it, I don't touch P. And as I said, robust actually has a built-in mechanism to help getting black and white. So in that sense, I don't need larger P's. It shouldn't be necessary in many cases. There are certain cases. So, for example, if you're doing material design and optimizing for stiffness there, then the gray is really a strong attractor that is really hard to get out of for various reasons I will not get into. But in that case, to sort of promote black and white, we sometimes use higher P. But otherwise, don't touch it if you can avoid it.
Do you always use the robust approach? Because it does carry more expense with it, right?
Yeah, I think almost always, because of its nice advantages with introducing length scale and stuff. But then, yeah, so who, of course, it's strong to say, but it's a factor of 3 in the worst case. You can run it parallel, so it's not that bad. Nevertheless, I would say, and there are many variations and also other ways to impose length scale, but I think still I'm anticipating the day where the robust formulation becomes obsolete and something else that works as well and stable and gives good designs will come up. So I think there's still an option for something even better turning up.
Yeah, because there are these sort of, other geometric approaches building on some of the ideas you presented here today. But my own experience, at least, is that they don't always work, and they just introduce even more parameters that need tuning.
So especially if you have to add, again, I prefer not to add extra constraints or adding penalization terms to the objective and stuff like that. You want to sort of come out naturally as it does here.
Yeah. And what about adding a constraint on a gray measure? Like the one you showed should be below something.
Yeah. Definitely. So that's actually one of the oldest tricks. I think Grégoire Allaire used it to get homogenization results with black and white. And Borval and Pedersen used it, and they actually showed that if you don't do the penalization just rho times 1 minus rho, but you do rho filtered times 1 minus rho filtered, then you actually get a very well-defined and black and white structure. So that's a very powerful way. Again, it has the disadvantage that you add it, or you either introduce it as a constraint or you add it to your objective function, and then it becomes difficult with the weighting. So again, they work very well, and they are known from the beginnings of topology optimization, but they are also difficult to control. So that's why I preferably want to avoid them. But I think I also said it last time, if everything else fails, then you could start that.
Yeah. Okay, and then we have one last question, and it's maybe not so relevant today, but you opened the box yourself. So do you think that level set methods offer any advantage over density-based methods to avoid the generation of void islands?
Well, I'm not worried about void islands because we have this virtual temperature method or nonlinear virtual temperature method. So if they appear, and we get rid of them. Level set approaches, well, so a real level set method cannot introduce a new hole, but it can certainly leave some region which is solid in the region. So it could happen just as well there as in density methods. So I wouldn't think that there would be any advantage there necessarily, but that would depend on the problem. But I don't see a big pro or con in that case.
Okay, great. That was it. Thank you so much, Ole. Thank you everyone who stuck around until the end. So we have one more session coming up in this lecture series. It's the 28th, I believe, right? No, that's a Saturday, 26th, sorry. So in 2 weeks and 1 day. And then sign up for that. And I can just now tease that I have gotten an agreement that we will also get 3 lectures on level set methods. So if you have questions specifically to level set methods, you can come back to that in the future. The exact dates and stuff will be announced on our various channels relatively soon. But that was just a little bit of news. And with that, I think I will say thank you for today and close down the webinar.
Thank you also from my side. It was a pleasure, and thanks for the questions.